Okay, this is my poster for the reading of sections 10.6 and 10.7. 10.6 was on hydrohalogenation of alkynes. So very similar to what we learned in chapter 9 with the hydrohalogenation of alkenes, we can have the Markovnikov addition of HBr across a triple bond. So if we were to do this, it would look something like this. So we have a terminal alkyne here reacting with HBr once would give us, again, the addition of Br on the more substituted carbon and the addition of a hydrogen on the less substituted carbon. And then if we were going to continue with that and add another HBr, we would see an additional Br added to the more substituted carbon and an additional hydrogen added to the less substituted carbon. So in our end product would be a geminal dihalide, again where geminal is referencing that both of the halogens, both of the bromines, have been added to the same carbon, and dihalide meaning two of the halogens. So the mechanism for this is going to look something like this. We would start with a proton transfer where the electron-rich pi bonding area is going to attack the hydrogen, and then bond breaking with electrons depositing on the bromine, forming the bromide ion. And then we have the intermediate here. And this intermediate it's rather unstable. We have this is a vanillic intermediate. Again, vanillic meaning that we have a carbon with that's pi bonded that has a positive charge. So anyway, we would see now nucleophilic attack from the bromide ion, and that would attach itself to this carbon. And then if we were to continue this, we would just repeat the process. So we would have proton transfer again with the pi bonding electron-rich region attacking the proton, breaking of the bond between the hydrogen and the bromide, forming a bromide ion, and then the hydrogen attaches to the less substituted carbon. Again, we have an intermediate that has a positive charge. So next step, again, another nucleophilic attack from the bromide ion attacking the carbon, and then we're left with the final product, which is, again, the geminal dihalide. We can also do an anti-Markovnikov addition of HBr if we have peroxide present. So we don't really have to worry about the mechanism of this, but we do understand that we can turn our alkyne into an alkene if we just react it once with HBr and the peroxide. And here we can have a mixture of E and Z isomers. And again, the E meaning that our higher priorities are on the opposite side of the pi bond. Here we have bromine, and then the rest of the chain on opposite sides of the pi bond. And then with Z, the higher priorities are on the same side. So bromine and the rest of the chain, being the higher priorities, are on the same side of the pi bond. Again, if we were going to react this further, we would see that another bromine is being added to the, again, less substituted carbon. So again, this is the addition of HBr, where the Br is added to the less substituted carbon. And that's what I have for hydrohalogenation of alkynes for 10.6. 10.7 was about hydration of alkynes, starting with acid catalyzed hydration. So again, very similar to what we learned in chapter 9 with acid catalyzed hydration of alkenes. It's a Markovnikov addition of a hydroxyl group across the pi bond. So an example here would be we have this alkyne. Our reagents, we have sulfuric acid, water, and then mercuric sulfate. The mercuric sulfate is just a catalyst, and then the sulfuric acid is our acid. And what we see here is the again, a hydroxyl group being added to the more substituted carbon, and that forms an enol, and the enol rapidly transitions to a ketone, and this transition is called a tautomerization, which we'll talk about here in a second. So the end product of this is actually a ketone. The mechanism, actually it's lengthy, but it starts with a proton transfer. So again, the electron-rich area of our pi bonding attacks the proton on the hydronium ion, which is our acid, and forming our intermediate, our charged intermediate. Again, this is a carbocation, but it's on a vinylic carbon, so rather unstable, which is it causes the reaction to be pretty slow, and that's why we have our catalyst of our mercuric sulfate, which speeds this process up. But anyway, the next step again would be the nucleophilic attack with the water, and it attacks that carbocation, and it forms our charged species here, similar to what you guys would be used to with the acid catalyzation, or catalyzed hydration of an alkene. So we need to deprotonate this charged species. We'll do that with water, and that gives us our enol. Now, an enol is simply a compound that has a pi bond and the carbon, a vinylic carbon with a OH group attached as well. So this is an enol. The enol then is going to go through what we call acid catalyzed tautomerization. And our enol here is going to go through tautomerization. So we have an acid molecule, or hydronium, and it's going to go through proton transfer. So the enol is going to, or the pi bond from the enol is going to attack the proton on hydronium, bond breaks, forming water, and the enol turns into an intermediate. So what we have here, and I mistakenly drew this double bond, so I tried to scribble that out. So the double bond's gone. We have a positive charge on the carbon because we've added a proton to this carbon. Now, this positive charge here on this carbon can be resonance stabilized. So these two structures here are actually resonance forms. So just showing the transitioning of the electrons to show the different resonance forms. So positive charge can go from the carbon here to the oxygen, where the double bond can form with this extra electron pair from the oxygen. So these two structures are just they're just resonance forms of each other. So the other part of the tautomerization is it's the addition of water, and water will act as a base in this case, and it's going to deprotonate the proton that's connected to the oxygen, and what that leaves is a ketone. So the tautomerization process is the enol turning into the ketone, with our acid being deprotonated by the pi bond of the enol, and then water deprotonates the intermediate. So basically what this is, it's a hydrogen that's moving from our oxygen to our carbon. So this hydrogen essentially is, you could say, moving, even though it's actually being deprotonated here. But we have a movement of the hydrogen. Is that what I want to say? Or I want to say not hydrogen, but pi bond. We have a movement of the pi bond between the carbons to the carbon and the oxygen. So that's what I was trying to say. So that's what we call tautomerization. Again, an enol turning into a ketone. And then the last part of 10.7 was hydroboration oxidation of alkynes. And again, this is very similar to hydroboration oxidation of alkenes that we learned about. It's the anti-Markovnikov addition of OH. And very similar to what we just saw, we can form an enol, and the end product, instead of a ketone, is an aldehyde. So again, the anti-Markovnikov addition, or the OH adding to the less substituted carbon, and that gives us the enol, and then the enol is actually base catalyzed into the aldehyde. So showing that right here with the mechanism. With our enol, it's our starting point. Hydroxide is going to deprotonate the enol, and that leaves what we call an NO8 ion, and the NO8 ion has two resonance forms. So my arrows here showing the movement of electrons to form the other resonance form. And then water is going to act as a proton source. So our NO8 ion is going to deprotonate water, which reforms the hydroxide, and then that gives us our aldehyde at the end product. And some other reagents that I've noticed through the reading that will identify this, other than BH3, THF, and then hydroxide and NaOH. Other reagents are going to be 9-BBN with hydroxide and NaOH, and then R2BH and hydroxide and NaOH. So that's hydroboration oxidation of alkynes. Again, it's the end product is an aldehyde through a base catalyzed tautomerization of the enol. All right, hopefully that was helpful. That was my posters on the reading for Thursday.